And we're live, I think.
Yes, we are.
Hello, everyone. I think we just posted a link. We did. So let's wait a few minutes for people to join. Can we see the comments there, Brok?
Yeah, sure.
This is Brok, by the way.
Hey, everyone.
Brok, I can't pronounce your last name.
Bucholtz.
There you go. Do you want to share your Twitter handle, Brok?
Yeah, it's @Brok_Bucholtz. Good luck spelling the last name.
That's the challenge.
Yeah.
So I see people in the live chat. Hello, everyone. I know we're late. It was Brok's fault.
I see how it is.
Yeah.
I'll just accept that.
We also have Elizabeth here.
I'll join this. So.
Elizabeth just walked in. It's like, there you go. Okay. How about we get started? There's a lot of people joining, which is very cool. So first, I think it's kind of weird that this is. We'll go back to the other one. You don't mind. Let's talk about deep learning. So the reason Brok is here is because Brok is firstly one of the folks working on the self-driving car nanodegree. He's also helping on the deep learning nanodegree, deep learning foundations. And he's a machine learning engineer. And he's been at Udacity now for, I'm giving no introduction here.
Around 6 months. Yeah,
6 months.
Pretty early for everyone else around here.
It's flown by, Brok.
It is, sure.
Totally flown by. So my name is Oliver. I work on the Udacity self-driving car project. Have been building with a bunch of folks here an open source self-driving car, as well as working on the curriculum of the self-driving car. And one of the main techniques that we're using to build the open source self-driving car is deep learning. Basically, can you, given a camera, given a nice GPU in the trunk, and a bunch of other stuff, can we predict steering angles using only machines? Turns out you can. Turns out it's a very difficult problem, but you can do such a thing, and it's very exciting. So actually, and even though the event title here is Deep Learning with Udacity Self-Driving Car, we're going to talk about fishing.
Yeah, fishing.
Aren't we, Brok?
Yes.
Not something you'd usually associate.
I don't even fish.
And maybe that's why this is going so well. Yeah. Not something you'd usually associate with deep learning, but I believe that deep learning is going to impact almost every industry you see out there. Anything that requires or can utilize prediction to get better at what it does will utilize deep learning. And as it turns out, there's a fantastic effort by an organization called I forget the name.
It's this animal conservation organization, specifically for fish.
Specifically for fish.
So they want to figure out what fish are getting harvested and like make sure they can make the count of what gets taken from the ocean, stuff like that. So it's very important that we know how much resources have been taken from the ocean. And basically this category competition is to find out what fish are taken out, actually specifically to find out what species have been taken out, and you want to categorize those from images on boats.
Especially when it comes to illegal fishing. It turns out there's a lot of illegal fishing around the world of certain species of fish. So basically there is a competition on Kaggle that asks participants to basically, given camera frames from multiple different angles, can you predict the type of fish that is on the deck? So when a fisherman catches a fish, it usually lands on the deck of the boat, and the camera
or back in the ocean.
Or back in the ocean. And the camera at the top of above the deck is then recording what sort of fish are landing on the deck. And basically, what happens right now is that these organizations trust fishermen to accurately categorize the types of fish they've caught.
Log it in a book.
Which is a very flawed mechanism, obviously, and this is why a lot of illegal fishing happens. So this challenge that Brok is going to talk us through, and we're going to show an example of what he's built. He's currently 400th out of.
It's not that great. We're just doing a simple CNN. We did.
Don't be so humble.
We did learning transfer with a GoogleNet. So if anyone else wants to be 400, just do that exact same thing.
Let me simplify what Brok just said as well. He said he's using a CNN, which is a way to say a convolutional neural network. Convolutional neural nets tend to work very, very well on images. CNNs, you can think of them as basically scanning individual parts of an image continuously at bigger and bigger sizes, and then looking for features in that image, looking for shapes, looking for colors, very many different types of things. And then because it's scanning at so many different levels, it can then start to predict what things look like. Even though, for example, when you look at a dog, humans can generally understand that a dog has big ears,
tail, four
legs, etc. But if you were to place an image of a dog in a very simple classification algorithm, when you put that dog in the bottom right corner of a giant image of a field, it might not expect to look there. So a convolutional neural net tries to basically look for the very minute details, and then together to understand that this is a dog, this is not a dog, this is something else. I don't know why we're talking about pets and animals so much, but let's get back to the fish.
Okay, yeah. So do we want to actually show results and take an image?
So what Brok has done, and his small team on Kaggle, is basically build a convolutional neural net that when input with an image, that it will accurately try and predict the species of fish or the lack of fish in an image. Yeah. So it will output a prediction that this is a, can you list them, tuna?
Yeah, we have those right here. It's different types of tuna, so it's albacore tuna, big-eyed tuna, dolphin fish, which is basically mai-mai, moonfish, short fin mako, yellowfin tuna. If there's no fish, then we also have a shark, and other. Other is basically we see a fish, we just don't know what type of fish that is.
Awesome. So you might be wondering, how does the machine know how to classify these things? Basically what you do is you collect a whole bunch of data. And this data that Kaggle has provided, in this case, is labeled, I believe.
Yep.
Basically you get an image and a label. Is there a bounding box?
No, but to talk about bounding boxes is basically on these images you have coordinates of where these fish are, and you use that with something like a fast RCNN, and which basically tries to predict where the fish is in the image, which makes it easier to predict what kind of fish that is versus searching the whole image.
Definitely. We're going to now show an example. Here's what we're going to do. I'm going to do a Google search for a tuna.
Okay.
On a boat deck.
Hopefully not canned. I can't predict that.
Let's not go that far. V2 maybe. I'm going to Google search. There's no magic, no trickery here. And I'm going to send that image to Brok. And then Brok's going to run that through his neural net that he's trained to classify these types of fish. This could go terribly. This could go well. I don't know which it will be, but let's find out. So I'm going to go on my machine right over here. Brok's going to...
I'm going to entertain you guys.
Can you change your screen to the share screen?
Share screen? Sure thing. Better hide a bunch of stuff.
Brok has never done a live stream before, just FYI.
Yeah. Okay, so we are going to run. That's this right here. I'm going to hide a little bit of my code there. I'm very paranoid about my code.
You should.
Don't judge me. Don't judge me.
So I am looking for an image right now. Keep in mind that unfortunately some of these are pretty gruesome. If you are squeamish about fish on decks, then this maybe isn't the live stream for you. Although I'll try and find a better image.
I could actually, I'll show them the pile of tuna that we were doing before.
Let's do that one first.
Okay.
So this is an image I randomly searched beforehand, and it turns out this one classifies very well. So if you look on Google Images for tuna on deck, you will see that this image comes up. So basically what's happened here is this the output right here?
Yeah,
this is the output. You highlight, double.
The name?
Just the predictions.
Oh, predictions.
So basically this output is the confidence that the neural network has that this particular image right here is a tuna, or rather is any of these things. So we've got shark. It thinks that there's a 0.07 chance that this is a shark, or 7%. And
No fish.
No fish.
Yep.
It's pretty certain, less than 1%, that this has some fish in it, which is great. DOL, what's that one, Brok?
Let me check real quick. I have to look up these categories. DOL, Maya.
It's pretty sure it's not dolphin fish.
I think it's that one. The other one does.
Oh, Brok. And bet is a tuna fish, a specific type of tuna.
Big-eyed tuna.
Big-eyed tuna. And it's 83% sure that this image contains at least one big-eyed tuna.
And that's as good as it gets, because if you have something that says it's 100% sure, you probably overfit. Probably wrong on the model. You might be right on the answer, but the model is incorrect. So Oliver right now is looking for a new image to test on.
I have one.
Okay, he's going to send it to me.
This is a tuna, and I'm going to send it to Brok. Here you go, Brok.
Awesome.
It's coming through. Now, this is not scripted. We don't know how this will go.
Not that one. Make sure I get the right one. Here we go.
We just saw the Slack name of the team Brok's working on, Save Nemo.
Say. That's not. I don't get a bunch of spam. Okay, so I'll download this one.
Yep.
Come on.
There you need to click this right one here.
Down from the cloud.
Brok's also never used Slack before.
I'm so nervous. All these people judging me.
They're very friendly, bro.
They will bite. Okay. Copy that into my folder where I've got all the images. Let's make sure this is on our server. So I'm actually running this on a remote server with the GPU, which makes things a lot faster. So let's run this again. It'll do both images. That's very good. So the first one, this is the one we're judging on. We are judging it.
So wait, let's walk through this one. So this TT03 is the one we just Google searched. So it's basically saying here that it almost certain not a shark.
Yep.
It's almost certainly a fish at least. A dolphin fish it is not. It is 45% sure that it's a tuna. Which type of tuna?
A big-eyed tuna.
A big-eyed tuna.
Just like the last one.
Other, it's almost certain that it's one and it's not something else that's listed. Yellowfin tuna, I believe, is 23%.
Yep.
So although not spectacular.
Nope, not spectacular. But
it's not bad.
It's not 100% sure though. Like this 83% sure is you can say that's pretty good. 50, like less than 50. Not so great. That's good.
But this is why we test, and one of the things that tends to make deep learning work as well as it does is data. Let's actually do a quick walkthrough of the data that you train your model on.
Sure.
So basically, Kaggle provided a whole bunch of images and labels, and you'll see that when we walk through the training set, the training data set that Brok has used. Let's go to tuna. Oh, I'm told that there's an NDA on this data set.
Yeah,
and
so I cannot show. But if you would like to see this, you can actually go to Kaggle itself, sign up, and you yourself can be a machine learning engineer.
Sorry about that. So let's do some questions.
Yep.
So based on this neural net that Brok just showed, let's go back to people view. Let's go back to.
You open up chat in yours, and
I've got the chat in mine. Let's go to people view for showing the camera. There we go. We're back. Let's do some questions. How long did it take to train the CNN?
So I'm using a GTX 960. I did transfer learning. So we already had a good amount of weights from GoogleNet.
Let's simplify, Brok.
Sorry. 20 minutes, maybe. I think 20 minutes.
Well, no. So basically, transfer learning is this idea that you can take a model that's already been trained. So, for example, something like GoogleNet is a model that was trained for a competition called ImageNet. Basically, up to Google trained this model to classify up to 1,000 different categories of things. So you can feed this model an image of a person, and it will say it's a person. A soccer ball, and it will say it's a soccer ball. And obviously, to train such a thing to detect so many things, that data set is huge, and the amount of training required is huge. So for a technique like transfer learning, you basically say, hey, GoogleNet is a fantastic thing that took Google a ton of time to build and train. We can take the benefits of that. We can
take credit for it.
We'll take credit for it. And then you train, or retrain rather, the last layer, where it classifies a soccer ball. Instead of classifying a soccer ball, you now classify a fish, or various types of fish. So to train, it took you about 20 minutes, you said?
Yeah.
And that's on a relatively good graphics card.
Yeah.
Okay, let's have a look. Questions. Why do they give us like 2 seconds before they go live? Yes, that is a good question. I believe there was an email we sent out, but we'll get better at it, I promise. Can you try different species to test the model? We can, and we should do another broadcast of Brok's model as he goes goes further in this competition.
Once I get the fast RCNN working, I think that'll be a much better job.
How big does the training set have to be on average? This is a tough one because there is no real right answer.
Can I answer that? It really depends on the complexity of the problem. If it's something that's very easy, then not that much data. If it's very complicated, like self-driving cars, there's a bunch of different rules out there, different situations. So the more the data, the better. And then you have different scenarios as well. So like for us, we were basically taking images from same perspective each time, so that makes things a little bit simpler, because then you can ignore like the shape of the deck and stuff like that, since it's from the same perspective. Where if you're taking from different perspectives, then you have these different objects you don't know whether to ignore. Is that a fish? Is it a pole? Stuff like that.
Very cool. So another question here is saying, Brok, your team is now at 504.
We got
1,200.
We're out of the 400.
What do you think other teams are doing in addition to your approach? That's a very good question.
Fast RCNNs, for sure. I looked it up a little bit. Sadly, I don't have enough time to do it during work, so I have to do all this stuff afterward. So I'm always lagging behind by a day or two to people. But yeah, definitely, I think fast RCNNs. So you have these bounding boxes, which are coordinates where the fish are, which you have to manually label. They don't give you that data. And you train a neural network to basically find fish. And once you found the fish, you can use that information to be like, oh, don't look at the whole image, just look at this part.
Very cool, very cool. So now we're going to switch over to talking less about fish and more about self-driving cars. So Brok, I sent you a video, which I'd like to play.
Sure. We're getting the video right now.
Let's get that up. There we go. You will have to switch the
share screen.
There you go.
Sure.
So we're sharing
I
screen.
think we can hold of this.
I'm not so sure. Can everyone see the video? Let's pause it for a second.
Okay, I assume so.
We're
literally YouTubing through YouTube.
Can you guys see the video that we're just playing?
I think there's about 10-second delay, something like that.
Let's see.
Okay,
looks like you can see it. Perfect. So one of the fun challenges in self-driving cars, ever since, honestly, Sebastian worked on cars in the early 2007s, 2009s, has been traffic lights. Traffic lights are everywhere. They were built for humans. They weren't built for predictability. They were built to optimize for human behavior. But machines need to be able to understand traffic lights, because they're obviously an integral part of how we navigate around the country safely. And one of the traditional challenges has been for a machine to detect traffic lights. So when we started the self-driving car project, we used a very basic computer vision solution. And solution is a word which I actually wouldn't use for this, because it didn't really work all that well. And there's a number of factors about why. It depends on your camera, it depends on the time of day, depends on if there's a truck in front of you, it depends on your technique for detecting such things. But in reality, traffic lights are everywhere. They're in different positions, which is even arguably more important. Sometimes you have multiple traffic lights per section that you are at. Sometimes they don't really work. Sometimes they flash yellow. Just a whole bunch of craziness. So what we've been working on is, in our effort to get to 100% accuracy in detecting traffic lights, is a convolutional neural network for traffic light detection. So
I know that.
Yeah,
I've heard of that.
The CNN.
Yeah.
Our previous solution attained, on a test strip of road that we have, about 63% accuracy in detecting traffic lights, which is terrible, frankly. That means that out of every 100 traffic lights, 37 of those traffic lights will be missed, which is obviously very dangerous, and obviously
maybe it's just optimizing speed.
Perhaps, Brok, perhaps. So we decided to build our own other solution using a convolutional neural net, like I mentioned. So let's watch this video a second. So we'll see some stuff here. We'll see it detecting traffic lights in the bottom left corner. We'll see it can't detect anything. It knows it's green. It's still green.
I am going fast speed though.
That's fine. Okay. Keep it going. I think it actually is already in fast. You can see this is what the real world looks like. There's lots of cars moving. There is different glares. This is actually dusk, so it's a rather difficult time in some cases for the camera to catch everything. There's lots of other lights. You can see lots of red here in other cars. You can see, actually, if you go back and pause that section very quickly to where we were, pause here. You can see on that right side, there are 3 traffic lights, all red. In fact, on the left side, there is also another red traffic light there. And you can see just how poor capturing these lights are. The tree on the right there is kind of really messing with the camera frame, so you can't really see the outline of the traffic light. But effectively, if we go to this blog post that I also linked Brok to,
this one?
This one, yes. This is a blog post in progress by Eric, who's on the self-driving car team. We scroll down, down, keep going, keep going. Just keep all the way. There we go. So this is a very, very small subset of training data. So basically what we did here was record a whole bunch of stretches of road around this area. Camera frames, steering angles, vehicle information, and everything. We then asked a whole bunch of annotators, humans who annotate data, to say, hey, tell us where the traffic lights are in this image. They used a combination, or we used a combination of machine learning to try and detect them ourselves, but humans are really, really good at finding traffic lights, again, because they're optimized for this. So you can see that there's so many different variations of the traffic light here, not just position, but also the actual signal. You can see some left lights here. You can also see the different times of day, different lighting conditions, different camera conditions. And this is, again, just a very small subset. So what we do is then feed this into a convolutional neural net, again, labeled that these are traffic lights. And we do that over and over and over again with a ton of data and a whole bunch of algorithms on the other side. And the output is that we can almost 100% of the time right now detect traffic lights. So if we go up a little bit, keep going. Here we go. So we can see here what the CNN is using. So it's cropping to this tiny frame of a traffic light, and in some ways enlarging the image. And this allows us to get better results because it ignores the rest of the image. It doesn't have to think about that light that the car has or anything else. It just looks at that particular traffic light and detects whether it's green, red, orange, or nothing at all. So there's a few places to definitely improve this. We can go back to the camera, front-facing camera, if you want. Okay. And we're back. There's a few ways to improve this. So as you might have noticed, we are annotating the data set. So this basically, like I mentioned, means that we are using humans to say this is a traffic light, this is not a traffic light. And when we think about not having that information, and we think about actually driving somewhere we've never been before, it becomes problematic to not have that information currently. So the kind of dream state that we hope to get to is that given a giant full-frame image, which could contain any number of traffic lights, any number of cars, humans, etc., we can 100% of the time detect that that is a traffic light. Now, that is one part of the problem, but it turns out there are even more problems in this space. So let's say we got to that place where we can detect, hey, there's a bunch of traffic lights in this area. Great. That's fantastic. But how would we know which traffic light corresponds to us, the car that's currently driving? Because obviously there are multiple different signals for different ways to navigate. You could have a signal to go left, you have a signal to go right, forward, everywhere.
And even other sides of traffic. So traffic coming from the right, traffic coming from the left.
Exactly. And even worse in some cases is the traffic light ahead, believe it or not. So if you're on a very straight road, which has a lot of traffic lights, when you stop at a particular traffic light, in some cases the camera can see the traffic light ahead. And you obviously don't want the traffic light or the detector to think, oh, that is my traffic light, not this one that's right in front of me, because that's very dangerous. So one of the other challenges that we face, which may or may not be a machine learning problem, is how do we know which traffic light to listen to? That's something we're actively working on, because when we think about a total deep learning solution for the car, you again hope that you don't have to annotate this sort of data to understand that this traffic light is here, and this one's here, and this one's here. I hope that made sense. I'm not sure it did, but let's hope it did. Not for Brok. It's too focused on fish right now.
You want to go fishing?
I don't, definitely. Okay. So let's have a look at the questions here. We have a few. Looks like Nemo team is 504th.
Ooh.
Just rubbing it in there.
I know, so that's why I didn't want you to tell the team.
So good question, Javier. I think I kind of covered that. What if there are several traffic lights in front of you with different colors?
Yep,
that's the kind of problem where you just need to understand which one you should listen to. How do other car companies solve this problem, like Tesla Autopilot? They don't solve it, unfortunately, right now. I've seen other companies try and solve this. For example, Audi, in one of their latest vehicles, actually has a hook into the transportation network at a very high level. Effectively, it's an API. Audi can hook into that traffic light without visually having to look at the traffic light and understand what it's thinking. It's understanding that it's going to go red or go green in a few seconds.
So basically, they know where they are in the real world, so they know what traffic signs in front of them.
Exactly, and that's almost an unscalable problem, I would say. I mean, it works great when the city is installing smart infrastructure.
Does not work everywhere.
Does not work everywhere. And I think one of the most important things that we need to get to in self-driving cars is predictability. It can't be that it works here and then suddenly a mile down the road it doesn't work, because people won't use it to do the previous mile if they feel it will stop at any point. Another question. You mentioned you want to detect traffic lights correctly 100% of the time, but I assume that 100% isn't quite possible, right? Is there an acceptable margin of error? That's a great question, because yes, that's why I kind of laughed earlier at saying like 100% is what we aim for, because it's just impossible. Humans don't detect 100% of traffic lights. That's why people go through red lights. People get distracted, people don't look. Cars, like trucks, cover their visibility. 100% is almost impossible. At least today. I hate to say anything is impossible. Acceptable margin of error, I don't think should be measured. And
they are doing it per frame, where we tend to just see it and have that knowing it's there in front of us without continuing looking at it. So they have to do it every single second.
Exactly. So I think in general, the measurement should not be the number of traffic lights detected or not detected. It should be the what's the word? The security of the car, the fact it hasn't crashed, the fact it's stable, the fact it's not hit any other cars.
Oh, you mean using a different metric instead of saying how many traffic signs, more like how well does it perform in the real world?
Right. Because again, for example, if you're behind a giant truck, missing that traffic light is not a big deal, because you're following that truck and making assumptions based on the truck's behavior. A good question here was, what about traffic lights that aren't circular, like the turn right arrow? So something very interesting happened when Eric was working on this problem. I asked him, did we record any data in the evenings? Because obviously people drive 24/7. And traffic lights kind of look different in the evenings. You obviously don't see the outline, you just see the big luminous light. And because it's dark, the light is obviously a little more visible than it is in the daytime. And he said no. So I thought, oh my God, Eric, what did you do? You idiot. And he basically said that using a CNN basically mitigated that problem. Because when you take a CNN and train it with a certain set of data in a certain set of conditions, one of the great things about a CNN that this is how humans think, is you look at the minute details of that pattern. It's pattern matching. It looks for something that is reproducible in multiple environments. So when it looks at a traffic light in the daytime, and then it looks at it in the nighttime, it's actually looking for a pattern that we use. We look at the light. We look at the green. We look at how voluminous that color is, the size of that thing relative to the distance, just a whole bunch of different patterns which we intuitively pick up. So when we think about not just colors of the traffic light, but daytime and also symbols like the turn right arrow, it actually in our tests has detected those things without being explicitly trained to say, this is a right arrow, this is a left arrow, this is different colors. So that's kind of that's the magic part of a CNN, and one of the reasons it works so well is that because it looks at those minute patterns that we again intuitively as humans pick up, it's able to detect things in a variety of different situations.
Interesting enough, it sometimes finds patterns we don't even realize. It almost overfits in the sense we don't understand what it's doing, but it's very good at finding patterns, and that's what neural networks are strong at.
Exactly. Good question here. Regarding traffic lights, why not use GPS to determine exactly the coordinates of the traffic light?
Good question.
Well, it turns out you can't really rely on GPS. So maybe this is a subtopic of self-driving cars, but in many ways, when we think about a car being in a location, it's really hard to know where exactly you are in the world, because GPS is not reliable. It can be up to 20 meters. In fact, in some cases, much more, thinking you are in a different place. And that obviously means that that traffic light that we think is here might actually be slightly to the left. And as such, that just becomes an undependable way to actually detect traffic lights. But it's an interesting topic because it also goes into the field of like, how much human annotation do you use? Because I could be wrong here, but I'm not sure there actually is a database of traffic light coordinates that you can just pull from somewhere.
Not that I know of.
Yeah, so you're probably relying on a human to say this traffic light is here, and then using that data in the future. So again, that becomes a very slow process. We get to map the world ahead of time before you can navigate that world. And this is, again, why deep learning is becoming very prevalent in self-driving cars, because you hope that you don't necessarily need to map the world ahead of time. What about unusual light behaviors, for example, blinking red? This is a great question. I don't have a good answer, frankly. We have tested with blinking yellow, but we have not actually used a CNN to do such a thing yet. But it's a very interesting field to understand how that is. And also just because there isn't a lot of training data available, you don't often go by a traffic light and see a whole bunch of flashing yellow, red lights. So
you gotta catch them in the wild.
Yeah, you gotta catch them. Gotta catch them all.
Oh boy.
I know. Once all cars are driverless, there won't be a need for traffic lights. Are they more important for long-lasting problems to look at? Well, that's a good question. The truth and one of the real problems I foresee in self-driving cars is that there's no way getting around the fact that there is a transitionary period. There is a place where there are always going to be, for at least the next 5-10 years, I would say, human drivers on the road. It just is going to be that way. And as such, the cars that we build to be self-driving today have to understand that any crash, any accident, any human loss of life is unacceptable. So it just has to be living in that world. Maybe 20 years in the future, maybe 15, I don't know what it is, but sometime when we can just replace the whole infrastructure of the country or the planet, whatever, we will get rid of traffic lights, because I totally agree. There's not many use cases for traffic lights. Maybe for pedestrians crossing the street, we still need some semblance of that. But maybe there's digital ways of doing that. You don't need a giant, bright yellow, green, red bulb.
Well, I looked at the past for that answer, actually, because when cars first came out and there were still people on horses, they were actually on the same roads together for quite a long time, until they started to realize just how unsafe it was for horses there.
In fact, if you go to England, there are still horses on the road. So,
or my hometown, middle of nowhere.
Where are you from, bro?
Middle of Wisconsin. I won't say where though.
You don't trust the audience?
They'll be judging me about that too.
Another good question here. Would this be susceptible to billboards with pictures of traffic lights, especially if the light is red? I don't know the exact story of this word for word, but there was a very interesting story about the Tesla Model S fatal crash, which was very sad, of the cameras detecting the side of a white truck as the skyline. It believed that that flat white surface was actually the skyline, and as such that it was free to be able to navigate into that space, or rather to not avoid the car that was coming into its space. I will say that CNNs tend to be very good, like I mentioned, of figuring out the difference between a flat surface, if it's not been trained on that surface, to a 3D actual traffic light, just because there's just differences in those things. Like nighttime, obviously, it doesn't look like a traffic light at nighttime because it's not luminous. But it's an interesting problem for sure. Yeah. We have alligators on the road here. Can you detect them? Yes, you can detect alligators.
Yeah, you can. Just like we'll be detecting horses on the road as well.
Yes, and
it's stuff you have to do.
Exactly. It's an interesting problem to think about detection of individual objects, because we could just train a CNN to detect alligators, but it turns out that if you go to any different country around the world, they all have different animal problems.
Deer.
In the road, deer, turkeys. I was talking to someone yesterday, they have a turkey problem.
I'm hungry, I'll fix it.
That's the third time someone's made that joke.
Oh my God.
But I think when we think about obstacle detection, we need to be able to detect that this is a thing that is of mass, that is dangerous to hit, that is very unclear. When detecting a red light, how does the car decide where to stop, given that sometimes there'll be several cars ahead of you and other times where there are no cars ahead of you? Great question again, and another challenge we've been facing. So yes, you might think that you can see a stoplight and be able to stop before the stoplight. But again, given that traffic lights were invented for humans, the distance between a stoplight and where you need to stop, the stop line, is very different for different traffic lights. In fact, in some cases it's way back. In some cases it's right next to it. It's just very different. And if you go on the roads, you'll notice that a lot of the stop lines that kind of divide between the traffic light and the traffic are very worn out. And because they're on the floor, right in front of you in many cases, it becomes a very difficult problem to detect them using computer vision. So the way a lot of people do this, and ourselves included right now, is you annotate them. Again, using humans to annotate this sort of data. So someone goes through a 3D map. In fact, if you switch, Brok, to that blog post again.
Share screen?
Yes, please.
That's
Go up to the very top. So this is a image of point cloud data. And if you look very closely, you'll see this is actually an intersection, and that there are traffic lights here. I don't know if you can zoom in. Let's click the image. It's not very clear exactly, but you can see this is an intersection, and that there's buildings, and that there are street lights, and if you look closely at the black part here in the middle, there are traffic lights. So basically what we do is we task humans with going through this 3D data and basically saying, where do you see this stop line and where do you see this traffic light, and annotate both of those things so that when we can see that, when we do approach that position in our car, we know that, hey, we're either behind a car, in which case we don't want to hit the car, so we keep behind it, or we're at a stop line, and that's such because it's red, we need to stop at this stop line. Switch back to the camera. But in essence, it's a really hard problem. Honestly, it's one that I think the industry is not necessarily underthinking, but I think it's one of those problems where the best companies that win this space will put a lot of thought behind scaling to different cities, not necessarily just annotating like crazy.
And it's definitely a solvable problem. It's within our reach. Just going to take some time
Exactly.
and a lot of hard work.
And as improvements to computer image happen, computer vision, sorry, happen, then I think we'll start to be able to better detect these sorts of lines. And also, I mean, as cities embrace self-driving cars, it's in their interest to make it easy and nice for self-driving cars.
Yep.
So if a self-driving car or just a car sees that that lane, that stop line is not visible or broken, it's in the city's best interest.
These car companies, these self-driving car companies can actually do is just send that data over to the government to be like, hey, these are lines we're not sure about. Can you fix these? Can you repaint these? We noticed that this sign doesn't work, and I mean, that's great data for the city to have to basically, like us, to tell them, hey, here's potholes to fix. You don't have to go out there. We've got all the data you need to fix infrastructure. So do we have another question, Over?
Definitely. Yes, we do. Let's see. When do you think we will see a commercial car that is 100% self-driving car? When will technology be there?
What are they saying, 10 years?
Well, it really depends. There are multiple answers to this question. 100% self-driving car implies that it handles every situation on the planet. It handles rain, it handles snow, it handles roundabouts, it handles no roads, it handles everything. And that use case is a long way out. We know that. Like it's 10 years away. Maybe it's hard. That's why it's hard to tell. Frankly, I like to be optimistic, but it's such a huge challenge that maybe it's 5 years if a huge advancement comes, or maybe it's 10 years.
So people are even bad for like estimating a week ahead of time.
Exactly.
So a question like that, when we say 10 years, could be 100.
Could be, well, hopefully.
Hopefully not.
But I hear what you're saying. It's totally right on, because it's such a difficult problem to solve, but things advance so fast and in some cases so slow that it's what I mean. You know, about what was it? 4 years ago, deep learning was a very, very niche thing. In fact, there was a ton of skepticism about it, even maybe 2 years ago, maybe 3 years ago.
I'd say about 10 years is probably a good number.
Yeah, so
people are being made fun of for doing deep learning.
Exactly. So I think understanding that means that we have a long way to go, but who knows? Is this image of LiDAR? Yes, that is the output of a LiDAR. Are there any courtesy situations considered when developing self-driving cars?
What situations?
Courtesy, such as staying in the left lane at intersection so that someone is trying to make a right turn.
Google actually had a problem with this at four-way stops. So as humans, we'll stop for a little bit and go, and the rule is basically you have to fully stop. So it got stuck waiting at this four-way stop sign because it was waiting for everyone to fully stop before it could go. So there is kind of these unwritten rules of the road that we try to match in the same way that humans are doing.
Very cool.
What's another question we can get?
So we have here, how do you think future car makers will deal with hardware failures? What should happen if the car cannot recognize patterns anymore? So one thing that we use on our car is a middleware called ROS. It stands for Robotic Operating System. You basically run that on top of Linux, on top of Ubuntu in our case, and ROS has an architecture which is basically meant to deal with failure. You build nodes, and these are asynchronous objects that control something. So for example, if you have in your car a few radars, a few cameras, all of those are individual nodes.
It's an expensive car.
It's an expensive car, very expensive car. And what you don't want to do, like this question is asking, is obviously just go into crazy failure mode if one of those things has a little glitch. If your camera goes off, you don't want the radars to suddenly freak out and turn off as well. So this has been thought of for a long time in robotics, how to build fault-tolerant systems. And something like ROS is something I'd advise folks to get used to if you're getting into self-driving cars. It's just kind of the industry standard.
Yeah, definitely industry standard.
If there are fish on the road, Brok has your back.
I like it. Who's that guy?
That is Miguel Rus.
I like you. Yeah, I'll detect all the fish on the road. I'll report it to the authorities.
Exactly.
I'll tell what species it is too.
Is a self-flying personal transport vehicle the logical extension of self-driving cars? I love this question because I'm very, very bullish on.
Oh, what's the question?
You don't listen to me, Brok?
I do not. What'd you say?
Is a self-flying personal transport vehicle the logical extension of self-driving cars?
Still with me.
Basically flying cars. So a vehicle where you can, as a human, step into it and have vertical takeoff, take you to your destination, land, and go somewhere else. I am very, very bullish on flying cars because they, as a mechanism of transport, have very much less to deal with than a self-driving car. When you're in the air, there is different axes you can navigate on. You can go up, you can go down, you can go left, you can go right. In a car, you obviously can't go down, can't go up, can only go left and right and forward and back. So I think the safety implications of that are awesome. And the speed implications for fast transport are just much faster than perhaps a road vehicle could ever do safely.
And it's actually a much easier problem to solve too as well. You don't have to worry about all these trees and people walking. It's basically you and other flying objects. Birds is probably like the biggest outlier out there. Hardest thing to detect. Yeah, that would be nice if I could commute to Udacity from flying car.
No, I'm very, very bullish on it. From I actually genuinely believe that there may be flying cars way faster than that 100% self-driving car that we're talking about.
5 years?
I think so. I mean, the way I think about flying cars is that it's in many ways a hardware problem. Self-driving cars are in many ways a software problem. And when we think about how, for example, China is very adept at solving these crazy complex hardware problems, I think we'll see a lot more advancement in these vehicles.
How about the energy though? Because it does cost a lot more energy to go up in the air than to drive.
It does. I've seen some stuff. I cannot disclose what stuff, but I've seen some stuff that tries to be incredibly lightweight, so that the cost of takeoff and battery life and all those things, being fully electric and all that sort of stuff is minimal.
Awesome.
But we have a long way to go. So I unfortunately have to end in about 6 minutes. So let's get some other questions in here. Actually, let's go to this one. Someone echoed your point, Brok. From an energy standpoint, flying cars are not so good.
Yeah.
They're already developing a self-flying human-carrying drone in China. They are indeed. How do you handle snow and ice? Well, I think this is where, to me, deep learning comes in. There is a lot of issues today with using stuff like LiDAR on conditions that aren't dry, perfect California roads. And snow and heavy rain have real problems with LiDAR.
And a lot of these, I will mention, the data about that is actually, we figure out what kind of traction we get from these roads, which is very important. So like when you're driving and you hit a slick, you as the human driver understand, oh, what to do. Slow down. Oh, I don't have as much control. And along with that, we also want to detect when ahead there is slick, there's black ice, stuff like that, and handle it accordingly. But yeah, that traction data is super important for a car to understand when it's in bad conditions, what to do.
Very cool, very cool. Why TensorFlow? What are the advantages of using TensorFlow versus other ways of creating neural nets?
So that's a good question. There's no huge advantage other than it's supported by Google, and it's becoming the standard for a deep neural network framework. It's exponential growth I've seen for job postings compared to other deep neural networks, and I'm basically placing a bet on TensorFlow, and a strong confidence that it will be the biggest deep learning neural network framework out there.
Cool. Let's take one last question. Let me look here. In fact, I'm going to wait for the next question to be posted. I'm going to answer that one.
Who's up next?
Let's make it good. Don't rush it.
Who's the guy on the left? Waiting. I think everyone's gone. They just left.
Oh, God.
It's just been you and me talking for the last 30 minutes.
It's Elizabeth just posting questions. Different identities.
Just to pretend like we're actually doing something.
Exactly.
I like it.
Okay, so since there isn't any other questions coming in, let's do one that's already on the list. Instead of completely depending upon CNNs to do the job, I guess it would be better to come up with an IoT ecosystem of interconnected cars and traffic lights and other signs on the road.
That would be a perfect world.
That's a snark answer, but the right answer, because it's a tough problem to solve from a budgetary standpoint, because when we think about who benefits from self-driving cars, the true use case of a self-driving car is probably not that humans own the self-driving car. It's probably autonomous taxis running around, picking people up and dropping them off and picking them up again. And in that world, then it's in the company's best interest to get the traffic infrastructure installed. And there's some weird, conflicts of interest that arise when that sort of situation happens. So,
yeah, because there's other problems too, like what protocol to use. And you have to make these servers that are always up and running. So now you're depending on these servers. In this situation, it's more peer-to-peer. So like, it's a difference of who's responsible for these self-driving cars. And I think putting the responsibility into the actual companies is probably the best way to do this.
Exactly. A whole rush of questions came in. I assume
I knew it.
Google didn't update.
Okay.
So let me choose one from here. Who's the guy on the left?
I knew it.
That's me. I'm on the left.
No, look.
Oh.
This is a different perspective.
Oh, yeah. Correct. That's Brok.
I'm Brok. Okay. That's all.
Oliver. At Oliver Cameron. At Brok underscore
Bucholtz.
I've
got 5 followers, so make it 6.
Yes, let's do that, everyone. Let's get him to double digits. Okay, last question here. Would it be worthwhile to learn to do CUDA programming for deep learning or other machine learning tasks?
We haven't seen really a good reason to do CUDA. Thanks to TensorFlow, you can do just about anything deep learning in it. It's very great in the way it's kind of modularized. So like if you wanted to create a new node, so if you wanted to reinvent convolutional neural networks, you could do that in TensorFlow.
Definitely. Fantastic. Okay. Unfortunately, we have to go, but it's been fantastic speaking to you guys. Very, very excited about deep learning and very excited about the students in this particular NAND degree.
Thanks for having me.
Yeah, thank you. You're supposed to let me say thank you for Brok for being here.
Thanks for being here, Oliver.
Thank you. Really appreciate it. He's going to go detect more fish now and hopefully get above 500 position.
Yeah, I will.
Slacking away over here.
I'll come back with my 1 position.
Exactly.
I won't be.
No. Maybe. Who knows? Cool. Okay. Thank you, everyone.
Bye.
Speak soon. Bye-bye.